And welcome everyone. So today we're going to talk about how to interactively search and filter Enamine REAL Space in KNIME Analytics Platform. So let's start with the use case or with the problem that we want to look at. So you would like to design molecules with a certain selectivity profile. I'm sure everyone or most of you have been there, since we know that you're medicinal chemists and computational chemists. You would like to find the molecules that are similar to the query molecules, so they have the like similar biopharmacophoric features, for example, but you don't want that they are too similar, so that they're not identical. You would like that the molecules have different skeleton, that they have different scaffolds, that for example, the linkers also of the molecules are different. So what could be the solution? We will ideally would like to first interactively explore the data that is available there, and then pick the query molecules. After we've done picking the query molecules, we can just put them into the search through, for example, Enamine REAL Space using FTrees similarity algorithm. So the one that uses like pharmacophore-like similarity. And at the end, we would like to explore results and prioritize the compounds. The tool we're going to use for that today is KNIME Analytics Platform. So yeah, I assume you probably heard about that one. So that's an open source software for data analysis, visualization, and reporting, and it is based on the graphical programming paradigm. What does that mean? So instead of writing the code for each data processing operation, so for example, reading the data, or like here on the slide, you can see like the small note that shows our RDKit salt stripping, so like cleaning up the molecules. You have a node that performs each certain operation. And then you combine these nodes into a workflow, and that would be like your program. In KNIME, natively, there are over 2,000 nodes embedded that allow you to do different data processing tasks. So for example, you can access the data from different resources. You can perform different operations to transform the data, and you can also then analyze the data. So you can either like apply different machine learning algorithms, or you can visualize the data. Or like at the end, after you've done your analysis, you can also deploy, for example, the results of the analysis. So in addition to working with normal sort of usual data types, such as numbers and text, KNIME allows one to work with certain more complex data types, for example, as chemistry data types. So all the possible mol files, SDF files, like SMILE formats, and so on. And this is allowed through a variety of extensions. So some of them are open source extensions for cheminformatics, such as those present here on the slides, RDKit, CDK, like the Erlul nodes, those from Vernalis, and so on. They come as part of community contributions. And also there are many commercial extensions that allow to perform those cheminformatics and molecular modeling tasks that you are used to do like in your everyday basis, and integrate that functionality in the workflows. So for example, there are BioSolveIT extensions that we're going to use today. There are Chemaxon, Cresset, Moe, Schrödinger, and many others. So at this stage, we would like you to actually fill another poll to tell us what is your experience with KNIME.
Yeah, to make it a little bit easier for Daria, we're wondering how experienced you are with KNIME. If you didn't use it before at all, if you've seen it, if you use it from time to time, or if you use it very often, or if you consider yourself a power user, don't be shy. You can call yourself a power user. It will be appreciated today, definitely. So
That's true.
yeah,
We'll also learn.
that's true. And so I will close the poll in 5, 4, 3, 2, 1. And so we have people who use it from time to time and might be happy to learn a little bit more. For those of you who consider themselves as not ever used before it or just seen it before, we've put in the handouts section a little PDF file that shows you the first steps you can do in KNIME and helps you to install nodes and so on. And with that, I'm handing back to Daria, and she will start the demonstration.
Yes, thank you. So now I switched to the KNIME Analytics Platform. So this is how the software looks when you open up. It greets you with the welcome page, where you can get the links, for example, to the Learning Hub, to the Quick Start Guide, what you should start do, and also to the most recently used workflows by you. So, for example, one of my most recent ones today, you can see are like the demo ones that we will be going through today. On the left of the window, you would see the node repository, and the KNIME Explorer window. So the node repository is the repository that actually gives you access to the nodes that perform different data analytics tasks, such as like reading, writing, manipulation, and so on. In the Explorer window, you can get access to the sort of data file system within, like from KNIME Analytics Platform. Then in the bottom, you will have the view, which is usually like the console menu. So that tells you like, okay, what's going on. So if you see some warning messages or just like debugging messages like I have here, and also if you can add many more other windows there. And on the right, you usually see the node description window. So I would close the node description window for the time of the webinar so that we have more space for actually looking at the workflow. And I will also minimize here the console window. So let's have a look at one of our demo workflows. So here is the workflow I prepared for interactively searching and filtering Enamine REAL Space. So we'll start with a data set of several compounds that are active on the serotonin transporters. So let's have a look at the data. We right-click on the node, and then we go to Read Table. So here is my data table. It contains 104 molecules, and those molecules were tested against 5 different serotonin transporters. So here are the transporters. We extracted this data from Campbell database. And so all of those 100 molecules were each tested against each of those 5 serotonin transporters, and we provide their pKi values for each of them. Let's have a look at the interactive view. So how can we actually interactively explore the bioactivities of these molecules? For that, we prepared a composite view that is hidden in this wrapped meta node. So I will click on Execute the node and Open Views. So I right-click on the node, and then I select the menu Execute and Open Views. And so now there will be some data processing going on, and I will go in it in detail in a few minutes. First, I would like to introduce to you the interactive view. Let me make it a little bit lighter. So we will see here several elements, graphical elements. So the first one here at the very top is the parallel coordinates plot. And as each of the axes, we see the pKi values against each of the serotonin transporters. Let's go a little bit further in the view. What else do we have? We have on the left, we have a heat map that shows to us the pKi values using the color scale, so from blue to red. And in the rows, we have the data rows, so we have compounds, and on the columns, we have our transporters, and the activity of each is presented in a color scale. Then on the right from the heat map, we have a cluster view, so hierarchical cluster view. And here the compounds, so each of the compounds, here the AITs are on the bottom, they are presented in a tree view. And they were clustered according to the values of the according to their pKi values. So, and in the bottom here, so currently it says no matching reagents found, and this is and it would show here as the compounds themselves once we select one of them in one of the other views. So let me have a look and let me show you how to actually interact with this view. I go back to the parallel coordinates plot. So let us have a look. For example, if we pick one of the axes, like one of the lines on the parallel coordinates plot, we see that it gets selected. Then this row gets selected in the heat map. It also gets selected in the view of the hierarchical cluster. So there it is. And it also shows up here as a tile. And as a tile, then it just shows me the picture, so the image of the molecule, as well as all the 5 pKi values. So personally, I really love the parallel coordinates plot because it allows filtering on multiple chemical properties or in multiple properties in general. So what does it mean? So for example, let me just increase this slider so that I select a little bit more compounds. So for example, that having high pKi values on the Campbell 225. I don't remember exactly which subtype of the serotonin receptor transporter it is. So now I go down, I see there were quite a few molecules, several molecules selected. So, and let me now select, for example, another molecule, so another range. So on the another axis, activities of the Campbell's 3155. So now I have the molecules that have sort of higher activity on the third target and low activity on the serotonin transporter 3155. So what are those molecules? We have them here below as the tiles. So we see that they are they are different in their chemical structures, so probably they will be good as our query molecules. What we can also see that those molecules will be in our heat map. So I'm just literally dragging through the heat map and moving it to see where exactly those molecules are. So, and I see them selected here and highlighted, they are highlighted in bold. Yeah, so there were 2 here, and there was also one in the top. And also those ones I can see where they are in the cluster view. So let me go back to the cluster. And just maybe I need to either decrease or increase the size and move a little bit through the view so that I can find them. So there they are. There are two molecules here. They're those like orange ones. Let me enlarge it a little bit more. And one molecule over here. So you can see that they also, like this one and this two, they belong to two different clusters, so would be good queries. Okay, how was that built? So what happened? Let's go inside the activity clustering rep meta node and explore what are the nodes that allowed us to build this interactive view. So in order to open this rep meta node, I need to press Control or Command if you are on Mac, so depending on your operating system, and then double-click the node. So and here are the nodes that are inside my rep meta node. So here is the parallel coordinates plot JavaScript node that allowed to build the parallel coordinates. Here is the card view JavaScript that allowed to show our molecules as tiles. And then here are the nodes, this hierarchical cluster assigner JavaScript that showed us the clustering of the molecules and the heat map. Also the JavaScript, the heat map JavaScript node that allows to build JavaScript. How one would build that from scratch? I prepared a simple workflow to demonstrate you. So let me just open it for you. So it's called here build the view. So we have here the table, so exactly the same data set that we were looking at. So with this certain inactivities, so there's 100 molecules. And here I just connected two JavaScript views. So these are the ones that allow us to build those interactive views. So there is a table view. So let me execute it and open the view. So now I will do it not by right-clicking, but by pressing this like play and open view button on the toolbar panel on the top. So I executed, and now my table with the compound structures is opened in a separate window. Yeah. Now I can do the same for the parallel coordinates plot. I execute an open view, and I have here the activities as in the parallel coordinates plot. Okay, so how do I combine them in one view? That is quite simple. So we need to select those nodes. We right-click on them, and we say encapsulate into rep meta node. You get a message so that the warm nodes will be reset. So yes, I'm sure, because I want to create a rep meta node, and I will call it interactive view. So let us just execute this node and open the view again. So right-click, execute and open views. So now in the interactive view, we see the table with the molecules and the activities. And in the bottom, we see the parallel coordinates plot. So maybe that's not the perfect layout that I want to see, and I want to change it. How would I do that? I'm closing the view now, and I'll go inside the node. So I again open the content of this rep meta node. So Command and double-click. So here are my two JavaScript nodes inside. I want to change the layout. To change the layout, I need to press this square button to the very right of the toolbar. It will open a dialog to edit the layout. So currently I see that my layout looks like this. I have a table and then a parallel coordinates. I want to switch them. So I just need to drag one on top of the other, for example. Yeah. I can also change, for example, and put them on side of each other. So for that, I would need to pick, for example, those from the layout panel on the left from the rows. The following sign that has like those two panels with left and right menu, and I can put there, for example, the parallel coordinates on the left. Then I can put some other visualization on the right, and the table at the end, for example. Yeah, I think I will keep my visualization with parallel coordinates on the top and table on the bottom. And I will remove that element where the elements were in parallel. So let's have a look how our view would look now. So we already executed the node, so we now only need to open the view. And we can do that by right-clicking on the node and saying interactive view. Interactive view. So and we see the layout changed. So we have the parallel coordinates plot on the top and the table at the bottom. What about the interactivity now? So if we select something and the very on the parallel coordinates plot, we see that the table gets this blue icon on the very left corner. And it actually means that some rows are selected. We can show that by going into the settings menu of the table view and telling it show selected rows only. So now only those rows which we selected in the parallel coordinates plot will show up in the table. And this can be very powerful. I mean, you can move and drag your slider, and only those molecules that fit, for example, the properties that you are selected, will show up here. So only those rows. So for example, now it's only one molecule that fits particular, like this particular criteria. And so on. So if you want to go back and show everything, all the molecules, there are several things you can do. So you can either go back to the settings of the table view, for example, and then click this show selected rows only. Yeah, so now everything will be on the view. So those that are selected, for example, like this row, and those that are not selected, like this row. Or you can completely remove selection by clicking on each of the axes on the parallel coordinates plot. So now none of the molecules were selected. What is important to remember? Usually after you have done something, so some interactive exploration, so let's pick, for example, these molecules. They're the ones that are interesting for us. You need to, when you want to close that view, KNIME Analytics Platform will ask you, what would you like to do with the selection? So would you like to discard the changes that you made in the view? Would you like to apply the settings temporarily, or would you like to apply the settings as the new default? So we will apply the settings temporarily so that they can be used in the next view. What happens then afterwards? Let's have a look at the output of this node. So I right-click on the node and go to the output. I get this additional column which says selected JavaScript table. And there I can sort the nodes. And so those that were selected, they will get the true. Those that were not selected, they will get the false. And so this way you can use this information, for example, in the row filter and choose those molecules for the further analysis. And this is exactly what we did when we looked at our demo, at our interactive view for the selectivity profiling. So let me go back to this view. So remember we had this parallel coordinates plot with the 5 activities against 5 different targets. So we picked these 3 molecules that are active, like have higher activity on one and lower on another one. So here they are. And again, so I'm closing the view, and I want to apply those settings so that those molecules will be used as the query molecules. We go back to the workflow. So now if I open the output of this activity clustering web meta node, here there are my 3 molecules that I selected. So this would be exactly the molecules that we use as the input to search the F3 fragment space. And this is done in the Search F3 Fragment Space meta node. So I will not run the analysis right now because for each of the molecules it might take from 2 to 4 minutes, but I will walk you through what happens and we will have a look at the results in the while looking at the executed version of the workflow. So we go inside the node, the Search FTrees Fragment Space, and this is one of the nodes that is provided by BioSolveIT. So you can find it here in your node repository. They are nicely sorted by alphabetically, so here it is. So what are the settings? We have a query column, so this is our molecules. We also have to provide information which actually space we're going to search, and we're going to search the one that is provided also by the BioSolveIT. So that's the part of Enamine REAL Space. And here we can define the threshold, so what are the settings that we want to apply. So what is the minimum similarity that we should find, and what is our target similarity? So after we pick that, we click OK, and we can run the F3 similarity search. So afterwards, we will generate the 2D coordinates for the hits, and we will generate also the Morgan 2 fingerprints for the hits. That will allow us to compute, in addition to the F3 similarity, the Tanimoto similarity, so that we can compare it. So let us have a look at the results. So I have the F3 similarity search. So for that, I go from my demo view 1 to the demo view 2 workflow. So here you see my Search FTrees Fragment Space meta node is an executed state. So I can go inside. Let's have a look at the result of the Search FTrees Fragment Space meta node. So, and click on the similarity matrix. So what is how does the output look like? So we have here the first 2 columns provide us the query number and the query name. So the query name is our Campbell ID of the query molecule. The number is just the number in which it occurs. And here are the hits. So we extracted up to 1,000 hits for each of the molecules. And here is our molecule. And in the column similarity is the F3 similarity value. Also, in addition, there are a few other columns that provide, for example, the reaction ID and the reagents, because in Enamine space is built on the reactions, so you can, for almost everything, so if the compound is not provided by itself, you will provide, it can be provided by the certain reactions that are enumerated there. Okay, so I'm using here the column filtering so that I will only keep my hits and the reaction IDs. So then I'm generating the 2D coordinates for the hits, and I'm generating the Morgan 2 fingerprint so that I can perform the fingerprint similarity for each query molecule against each hit. So in this one, I'm doing with the fingerprint similarity node from Indigo, and this is part of the community contributions. Or I haven't actually pointed out that I have used quite a lot of RDKit nodes, and these are the part of the community contributions of the RDKit extensions. So these ones can be found under community contributions, and then here are the RDKit nodes, for example, and here are the Indigo nodes. So, okay, I generated the fingerprint similarity. So this was a simple Tanimoto similarity on the 2D fingerprint. And here are the collected results in a table. So I would like to have them in a little nicer view than just a table, so that this view can give me something. So I built an interactive view for that. Let's have a look at that just now. So I go back to the workflow. So, and I will execute the node explore results and open the view for it. So while it is doing it, you probably noticed that I have this node that tells renderer to image. And this is a very important step if you would like to display your chemical structures as the images on any like web-based application. Because without if you don't do that, then the chemical structures will be simply portrayed as strings. And this is not something that is like you have to do only while working with KNIME. You would need to do it like whenever you want to build any web-based application. And so in the meantime, the view has executed and opened. So what do we have here? We have an area like several range sliders. So for example, slogP, num HBA, num HBD. So they represent the computed physchem properties. So corresponding lipophilicity, number of hydrogen bond acceptors, and hydrogen bond donors. Then on the right, we have a scatter plot, which portrays the Tanimoto similarity versus the FTree similarity. And then on the bottom, we have the table, which will show us the matching hits. So currently it is not showing us anything. And why is it not happening? Because we have the settings there to show only those rows which will be selected in the view. So let's have a look. So let's pre-filter our hit list a little bit. So I think I would like to have a look at the compounds that have lipophilicity, for example, from 2 to, for example, 6 and 5, that would have at least one hydrogen bond acceptor, but maybe not more than 4 of them. And you see, every time I move the slider, the amount of dots in the scatter plot decreases. Because all these filter events, so they're happening in one, it's all happening in one composite view. So all these filtering events that are happening, they're sort of fed to the other views that are present in the same composite view. And now let's have a look also those that have at least one hydrogen bond donor, but maybe not more than 2. Again, we have a little bit less. So let's have a look at the compounds that we think interesting. I think it would be very interesting to look at the several use cases. So for example, something that has high similarity by FTrees and by Tanimoto. So let's have a look here. So yeah, this is like almost identical molecules. It only has like this one metal group on the side. Makes sense. And then now let's have a look at those which have high similarity with the FTree search and low similarity with the Tanimoto. Maybe that's too many. I'll do a few molecules so we can go through them. So I selected them. So these molecules have at first like the desired properties, plus they have the desired similarity. And so here they are. We can see that they do look differently. So for example, here we have some different linkers in the heat molecule compared to the query molecule. This one looks very, very different from the query molecule, like this one as well, and so on. So this way we explored and probably found a way to find interesting for us hits. So I will save this selection. So I have, let me have a look how many. I have picked 6 molecules. Okay, so I close the view. I apply those settings. Okay. Now the only thing that is left is just to write those molecules as, for example, an SD file. So once the view is applied, so I can write those molecules as the, for example, similarities results SDF. So we'll write my query name, similarities, and some properties. Okay, I will put it running in the meantime while the view is executing. So it's executed and the results were written. So here I have my similarity results SDF, so I can see it in my KNIME Explorer. Okay, so we've done with the demo. I'll just go back to my slides to quickly summarize that for you. So everything what we learned so far was the workflow that we built. We built it using the analytics platform, that is the open source tool. We used KNIME extensions and KNIME integrations. We used the community extensions, which are also open source, as well as we used the partner extensions for that, which were from the BioSolveIT. What we also quite often get a question then, what is the KNIME server? And this is the enterprise solution, so enterprise software product that facilitates collaboration, automation, managing, and deploying of the workflows. So in particular, it would allow you to share, for example, the workflows, the nodes that you built, those like in rep meta nodes or meta nodes. It would allow to log them. It would allow you to manage access to them and to the nodes and workflows in different applications. It would allow to execute the workflows, for example, remotely, and perform scheduled execution. So if you want to run those jobs, I don't know, every first Monday of the month. And of course, it also allows the web enabler allow to put the workflows on the web. And for example, all of those nodes that allowed us that showed us those interactive views, composite views, if you deploy the workflow to the web portal, this would be like a single page on the web portal. So who are working behind that? So that's company KNIME. So we are around like 70 people working in offices, like in 4 offices around the world. If you have any like further questions regarding the software, like KNIME Analytics Platform, community extensions, partner extensions, the company, the software as well, please come back to us. We'd be happy to tell you more. There are quite a lot of resources available on the web. So especially, I think KNIME Forum is one of the really best things to do. So if you have the question, because our community is very, very active, and most often the question was already answered. So there are also, so you can just Google through it, and probably the first answer will be from our forum. And of course, we provide a lot of documentation, and we make new learning courses constantly, working on that. So that's a way I would like to summarize what we learned today. So we combine the open source and commercial software to solve our use case in KNIME Analytics Platform. And hopefully I was able to show you that you can easily adapt it to your other use cases and to the other data. We interactively explored and filtered available data. And we also learned how one can build such an interactive views in KNIME Analytics Platform. So before I would get to the questions, I would like to invite you to our KNIME Spring Summit, which will take place in the mid to the end of March, so March 18th to 22nd, at the Berlin Congress Center in Berlin, Germany. So during the first 2 days, there will be different one-day courses, so that allow you to learn more and about the different functionality. For example, there will be text mining session. There will be definitely session to build to work with the server as well, to build interactive views. And then on Wednesday and Friday, there will be summit sessions where we, as well as our community, will present different use cases of interesting KNIME applications. And we also thought that, to provide, it would be nice, and we'd like to provide the discount for the registration that is valid till the February 4th. It is the BioSolveIT 25. So, currently there is also an early bird registration available that is like of 20%, but if you use the code from today's webinar, the code, that will give you the 25. So with that, I would like to thank you. I would be happy to answer questions if there are.
Yeah, Daria, thank you very much for your interesting talk. Before I forget to invite you, we have the next webinar already scheduled, so it's going to be on 20th of February, and it will be held by Professor Matthias Rareif from the University of Hamburg, and he will talk about machine learning in the context of bioactivity.